Well, hello and welcome to the Honest Investigators Talk Shop Show. I'm your host, Doug Bundy, president of the Larson Research Center, where we're unveiling the universe of motion. Now, today is Thursday, January 21st, 2016. We're redoing last Saturday's lecture, which was plagued with technical difficulties. And let me turn the volume down here a little bit. Got somewhat of an echo. They couldn't read the slides. Everything was a mess. I was really embarrassed, but due to personal circumstances, I wasn't able to do anything about it until today. So here we go. Once this show is over and recorded, then the earlier one will be deleted. And I apologize for that, but I tried a new technology where I could do a picture-in-picture kind of thing while I was presenting the slides, and that didn't turn out so well. The colors didn't show up, and there was all kinds of ugly things that happened. So as a result, we're trying to do better. We're just going to share our slides. There won't be any picture-in-picture, but we really don't need that anyway. So as I announced in that earlier show last week, I am presenting this lecture as the third lecture following the two that I presented 9 years ago. At the end of my lecture 2 then, on the coming revolution of fundamental physics, I said I would present this one on scalar mathematics, and then never got around to it. But so now we're trying to get that done. The videos of both lectures 1 and 2 that I presented back then are now available on our YouTube channel, the LRC Physics channel, as we call it, as well as at our website, lrcphysics.com. You can just look in the menu on the left there and find LRC lectures. And that has the actual slides synced with the video. So even though I'm going to delete it, for those of you that went there, you were able to see the slides plainly. But I'll post all of our YouTube videos on our website that way, along with the slides, so that it's a lot easier to follow than sometimes it is on the video. But I also explained then last week how we here at the Larson Research Center, or what we call the LRC, refer to the Newtonian-based program, that is the traditional mainstream-based program of theoretical physics, as the legacy system of theory, or the LST. And though that might seem to be a little presumptuous, it's necessary a lot of times, because we try to compare and contrast the difference between the two, which is a lot of times very useful. But so we call that the LST, and then the mathematics they use, which are vector-based, based on motion that moves from one location to another in one dimension at a time. We call that the legacy system of mathematics, or the LSM. So you have those two, or three: LRC for the Larson Research Center, LST for the legacy system of physical theory, and then the LSM for the legacy system of mathematics. This not only helps us distinguish between our system of theoretical physics, known as the reciprocal system of physical theory, or the RST, and our scalar-based system of mathematics, known as the reciprocal system of mathematics, or RSM. But it also makes it easier to refer to them in our speaking and in our writing. So it's only 5 acronyms that you have to learn, and they're real easy. So anyway, I wanted to get that out of the way right away. So in this part 2 then of our third lecture, Scalar Mathematics for Scalar Motion and Scalar Motion for Scalar Physics, we begin the journey of unifying the LRC's RST, that's reciprocal system of theory, based scalar motion theory of physics, with its RSM, reciprocal system of mathematics, based scalar number theory of mathematics. So we want to begin then with our slides here, and we'll try to make it a lot better. Hopefully this will work better than the other approach that we had. And like I said, we won't have a picture-in-picture, but you'll know it's me talking. So we call this a multidimensional scalar number system. And again, the name of the program is Scalar Mathematics for Scalar Motion and Scalar Motion for Scalar Physics. This is Lecture 3, Part 2. So the thing that we want to understand is that it's based on the reciprocal system of theory. Of course, we can't go into it on every program, but there's plenty of resources on our website. And actually here, if you go back to those prior lectures that I gave 9 years ago, there's a lot there on that as well. But you can then see that there are two postulates, fundamental postulates for the reciprocal system of theory. And the first one is stated as follows: the physical universe is composed entirely of one component, motion, existing in 3 dimensions in discrete units and with 2 reciprocal aspects, space and time, close quote. Well, this is these are from this postulate in the second one, which we touched on a little bit last time and we'll refer to more in the future. These 2 postulates make up the reciprocal system of physical theory, that the author of which is Dewey B. Larson, and he's the namesake of our research center here. And so it's important to understand these, that they constitute, these 2 fundamental postulates constitute the reciprocal system of physical theory. Everything we do is deduced from these postulates. So that's extremely important to understand. And from this first postulate, we've deduced the motion entities and combinations of them that form the observed particles of the standard model of particle physics, the LST, what they call the standard model of particle physics. And it includes quarks, the up and down quark, their antis, the anti-down quark and the anti-up quark, the electron and the positron, which is its anti-particle, and then the neutrino and the anti-neutrino. Now, they also have 2 other families of particles, but these are the stable ones. The others are not stable. They only last for very short time before they decompose, and we've chosen to not worry about that for now. And then over here you see is a mirror image of what's on the right. You've got the down quark here, and it is the mirror image of the down quark over here. If you have the up quark here, it's a mirror image of this, and then the positron over here is mirrored as well, and so on is with the bottom part. They're all mirrored except these 2, of course, which are in the center. So, and that's how the standard model works. They call it chirality, left and right-handedness of these particles, and that's an important part. But what's more is that then there's also 4 bosons, they're called, and you can see they're in a different configuration, and we'll talk more about that eventually. But this is the photon over here, and then you've got the W plus and minus bosons, and then an intermediate boson that seems to be a composite of the 2, which is called the Z boson. So that's important to understand. And these are all coming out of our ST combinations of motions. We have a suitor and a tutor, which we call, the suitor we call S, the tutor we call T. These are explained in our last lecture. We'll explain them in more detail, of course, in future lectures. But for now, just understand these as combinations of space and time. we'll get into, like I said, how that works eventually. But if you'd like more information right now, you can go to our lecture of January 9th. And that's also posted on our website, as well as here in our LRC physics channel. So, and then if you have any questions, of course, you're welcome to ask those. And in fact, I guess I didn't turn it on, but normally I plan on, at least we could do that maybe towards the end of the lecture when we'd have a question and answer period that you could Skype in and we can discuss these things. All right then, so in the field of mathematics and physics, it's very interesting how the two go together. It's a mathematical advance that enables physicists to do the major things that they've done. And last week in our program, Neil Turek, the president of the Premier Institute, I'm sorry, not the Premier Institute, the Perimeter Institute in Canada, explained the connection between calculus and algebra and geometry that came about through the most amazing formula in mathematics, as he calls it, and that's Euler's formula, e to the I pi plus 1 is equal to 0. Of course, you exponentiate the imaginary number I over pi, and that will equal -1, and that's the important thing that they came up with to tell us how marvelous that was. And that's true, they're right, but it's important to understand that it only takes us so far, and it's going to be useful to understand that when we compare it with when we compare it with what we're doing in terms of the scalar mathematics. So we want to understand that. So I've edited and cut down quite a bit that same video we watched last week. So let's watch this shortened version now.
Now I want to introduce a more bizarre mathematical character. And it took people 2,000 years to make the next great leap in mathematics. Okay, geometry was pretty important. With Pythagoras' theorem, you could build pyramids and structures, and architects wouldn't make a living without Pythagoras' theorem. But it took 2,000 years before the next huge leap forward in mathematics, and that came about with this strange character I. So all of a sudden, with this one extra character in the game, a problem that had seemed impossibly complicated and difficult, because some equations seemed to have solutions, some didn't have solutions. Now all equations were on the same footing, and they all had solutions. It's an incredibly powerful, simple idea. Once people had, now it relates to Pythagoras' theorem as follows. Once you have the idea that you have this guy I, now we are going to enlarge our space of numbers. We have a number x, which could be any number from -infinity to infinity, an ordinary number. And then we have another kind of number, which is a multiple of I. So, and we put the two things together. We say, I'm going to allow numbers which have a real part, the x part, and the imaginary part, which is the multiple of I. Okay, so the dimension, suddenly I've gone to numbers not being on a line, they're now in two dimensions. I can go along the line, I can also go in the I direction. And so I can go along x and up in y, and I get this number, x plus iy. So let's see it in action. So here we are, we have this circle, and the angle is the angle subtended by this pointer, and as the theta changes, this e to the I theta is running around. And you can see its real part is going backwards and forwards and backwards and forwards. And so if I use that real part to model a wave, which is also traveling upwards as its amplitude is going back and forth, I get what we call a sinusoidal wave. So the wave is now following this function, which came out of trigonometry, through this construction. And it turns out this is how nature works. Basically, everything that goes back and forth in nature can be described in terms of functions which look like this. In particular,
okay, we'll cut it off
Maxwell,
there. But that is extremely important, as he says. That's the this I, the invention of that, and then Euler's understanding of how when you exponentiate that, you get the square root of I, which is -1. So it's really an amazing fact, but it troubles a lot of people because of the concepts involved. They have, understood it in terms of the vertical axis, and so that makes a lot of sense when you get this rotation. But so, science never looked back. It's an amazing thing that what happened as a result of that. We got an understanding of waves. We got an understanding of then electronics came about, and so engineers were able to do that. We understood light. Then we found out that there were that light was both a wave and a particle, and so one thing led to another. But it was amazing how this advanced science. But that's not the end of the story. It turns out that there are 3 properties of numbers and magnitudes. They both have these in common. Physical magnitudes have magnitude, the value of the magnitude. They also have dimension. And then they have this called direction, or what we call direction in quotes, which is really a polarity. And it's important to understand this. You look at the notation as we see here. We've got, normally you don't put in there, which is the magnitude, but that is really an implied unit. Then you have 2 directions. The 2 stands for directions. And then you have the number of dimensions in the exponent. Now, that's really going to be important as we move on. And we're going to see how that's not recognized, that the 2 is not a magnitude in and of itself. It's actually the number of directions in which the magnitude is employed. But this is really important because nature doesn't extend in terms of numbers. They don't. Let me go back to that one. Let me back up actually to this one. When we're talking about rotation, the biggest problem that we have is in solving this connection between a wave and a particle. For the ancients, it was really a difficult case when they realized that you couldn't find an exact magnitude of a circle that matched the magnitude of a square. And so that was called squaring the circle, and it was impossible to do. But the other thing that happened as a result was that during way back in the days of Euclid, when he would provide 2 proofs of his theorems, one for a algebraic proof and the other a geometric proof, then also the same problem at about the same time with the Pythagorean cult. They had lots of things that were dependent upon numbers, but when it was discovered that there was no number for the hypotenuse of the triangle, then that eventually brought down their cult. And this is that conflict that extends even today between algebra and geometry, that this invention of the imaginary number I and the exponentiation of it over pi does not change. We still have this conflict between the quantum physics that are based on a fixed coordinate system, and the discrete units of that, and it has to have that fixed coordinate system, and then the theory of gravity, general relativity, which is impossible to explain in terms of a fixed coordinate system. So the two are totally incompatible. And that incompatibility, that conflict, is at the heart of the trouble of physics today. We've talked a lot about it on our website, and you can go there and find lots of articles about that. But it's also a problem for us, not just the legacy system. We have, in our first assumption, assumed that the universe consists of discrete units of motion. And so we've got to be able to explain gravity and all the different interactions between the particles that we have discovered come out of our fundamental postulate. We have to discover that or discover how then to reconcile discrete magnitudes with continuous magnitudes, along with all the rest of the world, the modern world and the ancient world, who've never been able to solve it. So our approach is to redefine really the number system itself. And now that gets us to this slide where we talk about the three properties of numbers that are actually the three properties of magnitudes. And that is, one, the magnitude itself, the dimension of the magnitude, and the direction of the magnitude. Now we talk about there being two directions inherent in each dimension. So that's what the notation is shown here. 2 to the 0, 2 to the first power is the first dimension, 2 to the second power, and 2 to the third power, 2 cubed. So we got those numbers multiplied, implied, because it's not literally shown most times. We could put the in behind the 2 here or in front of it, but it's the multiplier. So the magnitude multiplied in two directions, actually no dimensions, so that's null and void here. But in one dimension, there would be 2 directions in which that magnitude would be manifest. And then here there would be 4 directions in 2 dimensions that magnitude would be manifest. And here there would be actually 8, 2 cubed, in which the number of directions in 3 magnitudes in 3 dimensions, that this magnitude n would be manifest in. So we explain that in terms of the binary expansion of the Greek Tetraktys. And we can see a corollary to the geometry, and we'll see here in a minute how important it is. But recall that the binary expansion follows the format, if you will, of the Greek Tetraktys, and that's used in many ways. Pascal's triangle, it goes on, it's called. But what's happened is that it actually represents 0 dimensions, the entities in 0 dimensions, and 1 dimension on the next level. If you go down this way, you see on the right hand side, that's a 0 dimension, that's 1 dimension. This level, the next level is 2 dimensions, and this level is 3 dimensions. Of course, when you go to another level, you don't cast away, for instance, a point. So you've got a point in each one of those levels, but here it's a point in the middle of a line. Here it's a point in the middle of a line in the middle of an area, and here it's a point in the middle of 3 lines and 3 areas in 1 cube. So that's very interesting because the numbers correlate with the geometric understanding of points, lines, areas, and volumes oriented orthogonally. So it turns out then that this is a unification of numbers and geometry. The numbers of the Tetraktys actually correspond to a geometric magnitude of what we call Larsens Cube. You can see it here on the right. It's just a stack of 2 by 2. See, 2 this way, 2 into the depths, and 2 high. So it's a stack of 1 unit cubes, 8 1 unit cubes stacked 2 by 2 by 2. And each one of those then, though, corresponds to the dimensionality of the Tetraktys. You see that you can talk about the point here by itself, or you can talk about that point as an intersection of 3 lines, or you can talk about it as a point in the intersection of 3 planes. Seen here in the green, there's one oriented in each dimension. And then here's the horizontal one, 2 verticals in a horizontal plane that's shown in the green there. And then finally, there's 1 cube, you see, colored orange here, that contains them all. And the point is the intersection for it as well. So if we looked at the 3-dimensional figure here at the bottom, we see the point here in the middle. We see 3 blue lines oriented in orthogonal dimensions, and then the green indicating the 3 planes that are orthogonal, and then the orange showing the unit cube itself, when there's only one of those. So that's an amazing correspondence, and it's really important because this is mathematical and this is geometric. So with each instance here, we're saying of a 0D point, we have 3 instances of a 1D line again, 3 instances of a 2D plane, and 1 instance of a 3D volume. Very, very important, because 2 to the 0 is equivalent to a point. 2 to the 1 is 2, meaning a line with a point in the middle of it, because it's a dimension or a magnitude 1. Remember, there's an implied 1 out here that we don't see. So that was 1 magnitude in 2 directions of 1 dimension. So you can see that if you choose one of these, that from the point you go in 2 opposite directions of the 1D line. And then when you have the plane, choose one of these planes. Let's choose this one here. You see there's 4 units in that plane. If you draw from a line from the center point out to the diagonal of that plane, which would be the square root of 2, because these are unit cubes. So by Pythagorean theorem, we know that that would be the square root of 2. And there's a point in the middle of that plane, like I said. And then when we look at the 1 cube, we would have 8 out to the 8 diagonals, 8 diagonals out to the 8 corners of the cube, 4 at the top and 4 at the bottom. So that's a total of 8 directions in the 3-dimensional cube, or 2 to the 3. So that's an amazing correspondence, and it's something, as far as I know, no one else has ever pointed it out. We've been talking about it and employing it and using it to study our reciprocal system of mathematics for years here at the LRC, but as far as I can tell, we're the first, and maybe even still today, the only ones that are pointing it out. Now, when we look at that, though, we think of, okay, because it started, if we go back here, we think of starting with a point, right? In the Tetraktys, we expand out in these 3 other dimensions. Well, here we could think of that as well. An expansion from the point would give us a line, 2 magnitudes in 1 dimension, 4 magnitudes in 2 dimensions, and then 8 magnitudes in 3 dimensions. They're all part of that, but it expands out as a progression. So if we take that a long time, we start at T0 along a timeline, and then at T1, we would expand in 1 unit of time to this figure here. And then in time 2, we would, because this is a 3-dimensional progression, we would expand to 64, which would be, here you see it's 2 to the 3rd, then it's 4 to the 3rd, because it's, again, 2 directions. And so we add another magnitude in each direction. So this had a total of 2. So expanding out to the 2nd unit of time, that would be 4, and 4 cubed is 64. and 6 cubed is 216, and 8 cubed is 512. And if we were looking at the plane in there, you had 4, but then 4 squared, that's 2 squared. 4 squared is 16, and so on. It's 2n to the square, to 2n squared. And then, of course, for the one-dimensional line, it's 2 in each of the 2 opposite polarities. And then the next unit of time, that's 2 more, and then 2 more and 2 more. So it's 2 in the progression there. So if we look at just a regular number progression, we can go 1, 2, 3 and count up to infinity to any number n. Or we can count by 2s if we want to do 2, 4, 6, which would be 2n up to infinity. And we could do that in 3s. We can do it in any numbers. But as far as the numbers are concerned, they don't care. It doesn't matter. We can have any progression that we want, umpteen times infinity, whatever. So the numbers don't give us the same constraints that the Tetraktys and the three-dimensional expansion of Larsens Cube gives us. So that's important to understand. And it's also important to understand that we can't go any further than 3 dimensions as far as what can be observed. String theory in the LST community, string theorists want to go to 11 dimensions. If you count time, they want to go to 10 dimensions. And so they want to add 7 more dimensions of space to these 3 dimensions. And of course, they tried to do that, but then they ran into horrible problems. But if they would have listened to a man by the name of Raoul Bott, B-O-T-T, his theorem was proven that there is no physical phenomena beyond 3 dimensions. And that has to do with the number 8, and it gets really complicated. And maybe someday we'll explain a little bit about that, but we have talked about it on our website. So if you want to go there and look into it more, you can do that. But here it's important to understand that if we're talking about multidimensional numerical expansions, we would have to have them in 1 dimension. You've got to expand out in both directions of that 1 dimension, and 4 directions in the in a 2-dimensional expansion. And then if you go to 3 dimensions, you have to start with 8 directions. That's not an arbitrary decision. That's something that comes out of nature itself. And so we need to understand, though, that nature, of course, doesn't expand that way. It doesn't expand by numbers the way we can expand numbers. If we start with that 2 by 2 by 2 cube, though, there's something wonderful that happens. We find out that there, along with the expansion of the 2n to the third numbers, that what we call p to the third, or p cubed, make up these things. P cubed, or p sub 3 cubed, here I've written it as a 3D progression, that we get that number of cubes. We have 8, and then we've got a stack of 64, and then we have a stack of 216, and we have a stack of 24. But it turns out that we can define balls, volumes that just fit as a ball with a radius 1 inside that stack. So a stack of, as we start off with a stack of 8 in 1 unit of time, we have a ball with the radius of 1, which is the square root of 1. If we want to use Pythagorean theorem, we've got, we can explain that in more detail later. But then we have in using the radius of from the distance of from the center point to the 2-dimensional corner, which is the square root of 2 starting off, and then of course it doubles as we go on to 64, and triples as we go on to 216 and so on. But in the stack of three-dimensional cubes described perfectly by three-dimensional numbers, we have these three radii. One is equal to the square root of 1. The other is equal to the square root of 2. You can see it over here. It was hard for me to try to put all this together in one, so I separated this one out. And then, of course, the third one is this blue ball here, which I tried to see would have the radius as square root of 3 by Pythagorean theorem. You go from the center point out diagonally to that corner, which would define the radius of this ball. So we have three balls, one within the stack, that's the square root of, radius of the square root of 1, and then one with the radius of the square root of 2, and one with the radius of the square root of 3, that are automatically defined, if you will, by the expansion, numerical expansion of 2n to the third. So we could label these, we could label this the first progression, cube progression, which would be the 3D progression of the inner unit ball, which is what we call that one, black one there. And then we have p sub 2 cubed, which would be the 3D progression of the middle unit ball, which you see we've depicted here with radius square root of 2. And we've colored red. And then, of course, we have the blue one, which we would call p sub 3 cubed, which is the 3D progression of the outer unit ball. The outer unit being, again, the square root of 3, the middle unit being the square root of 2, and the inner unit being the square root of 1, which is equal to 1, of course. So that's an amazing thing now. So we've taken what we already know about numbers and geometry, and we found some amazing things, and lo and behold, one of those amazing things is that we've got continuous magnitudes associated with the discrete magnitudes, which should give us a clue, because this is the greatest mystery of all time in science and mathematics. So if we look at the inner ball scalar progression with square root of 1, then in that time 0, I mean time 1, time 0 is just a point. In time 1, then it's this ball of radius square root of 1. And then in time 2, it's 2 times the 1, which is 2, square root of 1, which is 2, 3 times that, which is 3, 4 times that, which is 4. And that will always just fit inside the stack, beginning with 8, but then the next one is 64, and the next one is 216, and the next one is 512. 2n cubed when n is 4 is equal to 512, and right on up to infinity, right? So that's amazing that we can specify within these different cubes of the 2n cubed progression this continuous progression as well. And then the same with the outer ball that fits, that the cube fits into. Again, it's a little difficult for me to show everything at once, so I'm trying to show them separately. But understand that this is called the inner ball because it fits inside the stack, and this would be the outer ball because it fits, or the stack just fits into it. So we have then a radius. It goes out to from the center point to the 8 corners of the cube, 4 on top and 4 on bottom. But each one of those is equal to, by Pythagorean theorem, the square root of 3. So then when we go to time t2, that's expanded, and the stack now is 8 by 8. It's 4 cubed. So we've got 64, and the ball that it just fits into will have a radius of twice this one. And this one would have one that's 3 times the original one, and this one 4 times. So then we have the middle ball that is defined by the 2-dimensional radius, which is the square root of 2. And so as the progression proceeds, then the radius increases as well, doubling. 2 times the square root of 2, 3 times, which is what? Square root of 8. Then this is the square root of 18, and this is square root of 32, and so on. So, I mean, there's no getting around it. This is not constructed. This is just an observation of how nature works. Now, if we take those, then we've got, we can call it the 0D. If we count that, normally we don't, that's just a point of no extent and no directions, no dimensions. So it's all zero. So by Pythagorean theorem, it would be the square root of 0, which makes no sense. But we have the 1D, 2D, and 3D numbers then in 3 dimensions inside this progression that we have just seen, that we're talking about, the 2n cube progression. And if we then took that as the square root of 0, then of course all these terms are 0 and doesn't make any sense. But when we go to 1D, you see, we in the Pythagorean theorem of 3 dimensions, we have 3 terms. But in 1 dimension, there's only 1 term that's populated. So that becomes our n. So n squared, the square root of n squared, since n squared here is 1, the square root of 1 is the answer. So 1-dimensional Pythagorean theorem would be the square root of 1. And we can plug that in. Here the point again is just a point. But when we plug that in as the implied multiplier of the 2 directions in our binary expansion of the Tetraktys, we're multiplying by the square root of 1, which of course is just 1. So 2 to the 1 is 2. 2 to the 2 times the square root of 1 squared is 4, and 2 times the square root of 1 is 2, and that's cubed is equal to 8. So that is nothing more than a different way of writing our familiar binary expansion down this way. But now when we go to the 2D case, again, we're in 3 dimensions. So now we have 2 dimensions of n. In the 2 dimension, in the 3 terms, we've got 1 that's not populated, but 2 that are. And so 1 squared is 1 plus 1 squared is 1. That's a total of 2. And 2 squared then is the answer. And we plug that in and as our implied unit. And we've got 2 times, for the 1 dimension, we've got 2 directions where that is a manifest, that magnitude is manifest. Here we have 4 directions. 2 squared is 4 directions in which that is manifest. And this would be then 2 times the square root of 2 cubed. And that's the manifestation of 8 units of the square root of 2. So you see how that works? And the same thing with on the 3D, where we populate all 3 terms of the Pythagorean theorem, and that gives us a square root of 3. And we plug that into our equations, and we get the results there numerically. So you see, while over here we have these balls defined, we also see that we can define them in the numbers of the Tetraktys as well. So now we've got the 0D point, we've got the 3 orthogonal 1D numbers, the 3 1D intersected lines there, the 3 orthogonal 2D planes, and 1 3D number volume, which would be the orange cube, and those all then correspond. But now we've got some continuous magnitudes associated with both our Tetraktys and our Larsens Cube, which we'll call RLC, the 2 by 2 by 2 stack of 8 unit cubes. All right, well then people say, well, but you got 3, you know, and that's, we don't see that. But see, you can understand that there's actually 14 units. If we ignore, we call it a generic unit maybe, where we ignore the difference in the dimensions, we actually have 14 units of magnitude in the 14 directions of the LC, normally when our unit is the square root of 1 or 1. And we can see this, that there are 14, because we can easily see in the orange cube here that there are 2 to the 3 or 8 three-dimensional directions, as I said, from the point in the center out to from the point in the center diagonally out to each corner of the cube, 4 at the top and 4 at the bottom. So we have 8 directions that are three-dimensional directions. Then if we collapse that, let's say, it doesn't matter how we collapse it, but let's say from top to bottom, we just push it down here to the bottom plane, or push them both up, from the top and the bottom, so we get the middle plane here, or we can push it from forward to back, or we can collapse it or push it from push left and right together. But in any way, we collapse the 3D figure to a 2D figure, and that gives us then the 4 two-dimensional directions. We can go from the point out to the diagonal, which is the square root of 2, and that would give us then 4 of those. And so the same thing, then we can collapse the 2 dimensions down to 1 dimension. Now we have 2 magnitudes, where before we had 4, 1, 2, 3, 4. Now we have 2. So we started with 8, then we got 4. Now if we collapse this down, we get a line that has 2 in each, 2 magnitudes in each, or 2 directions in opposite directions, opposite polarity. And then if we collapse the line to a point by pushing the 2 ends together, we come to a point that has no magnitude. So in total, then, we have 8 plus 4 plus 2 plus 0 is equal to 14 directions of magnitude that's in this Tetraktys. And it's also in this LC, in this Larsens Cube, this 2 by 2 by 2 stack, geometrically stacked unit that corresponds to our 2 n-cube progression, or it's the initial value of our 2 n-cube progression. So, and the same thing is in the Tetraktys, but the important thing is that we normally, when we think of the 2 n-cube progression, it's just we're only counting the directions that are three-dimensional. We're leaving out the 2-dimensional directions and the 1-dimensional direction. So if we don't do that, and we say, well, we've got 8 directions in 3 dimensions, 4 directions in 2, and 2 dimensions in 2, 2 directions in 1 dimension, then the total directions in the LC itself is 2 plus 4 plus 8 is equal to 14. So the LC's progression is actually a composite progression, and I'm stomping the floor here if I were teaching a class, consisting of 3 progressions: the 2n 1-dimensional progression, the 2n square 2-dimensional progression, and the 2n cube 3-dimensional progression. Now that's important to understand. We've never noticed it before. I try then to capture it in this graph by showing the multiple units of the LCs. So if we progress in our 2 n-cube progression, we start with 8, and then the next thing we go to is 64. But see, it looks like, well, you would combine these two. You got 8 here and 8 here. That's a total of 16. But see, these are not physical entities that we're combining. And so as a result, what we see here is a change in the number n. So this then would be 2n, because since these are units of motion, they would combine. And so if we drew them as 1, then these 2 units would become 1 unit with a point. These 2 lines here would become 4 units with a point in the middle, and these 4 2D magnitudes would become 4 in each direction. So 16, you see, and so on. So it's not actually the way we normally think in terms of physical entities, where this would be 1, and we add 1, we get 2, and we add 1, we get 3, and we add 1, we get 4. No, what we're really doing is changing the n here. So we got n equal to 1, n equal to 2, 3, and 4, and so on. So that's why in our progression we go 8, 64, 216, and 512. So if we look at that, we can see that the progression of the LC is actually a multidimensional composite progression of magnitudes. Over here on the left, we have in the 3D case, we've got 8 directions, and when n is 1, 1 cubed is 1, so 8 times 1 is equal to 8. Here we've got 4 directions, and when n is 1, 1 squared is 1, 4 times 1 is 4, and so on with 2. 2 times 1 is 2. So we have 14 directions that then give us 14 magnitudes. But when n changes to 2, then 2 cubed is 8. So 8 times 8 is 64. 2 squared is 4. 4 times 4 is 16. 2 squared is 2. Or not 2 squared, but 2 to the first power is 2. 2 times 2 is equal to 4. So now we still have 14 directions, but we have 84 magnitudes. And in this case, 258 magnitudes, and here 584 magnitudes of multiple dimensions in our composite progression. Now, I know that's a little bizarre, but if you think about it, you'll see that it's the only way that we're just too used to using the one-dimensional numbers. That this is taken as a one-dimensional number cubed. And so as we go on, we don't have a normally we don't think of a geometric equivalent. But if we did, it would be 1 here with 64. It would be 4 by 4 by 4 deep, which would be 4 cubed. It would give us 64 cubes, not 16, and so on with the rest of them. So that's important to understand as we go on here. But now, what we want, so now we're understanding a little bit more about the actual discrete progression and the units that are involved in it. But then we also have the continuous progressions that we just saw with the square root of 1, square root of 3, of 2, and the square root of 3. And so those are all cubes, and cube because they're volumes. So we're talking about a number in the exponent of 3. But see, we can write it differently. We can write that same thing, 2 directions times 1, but now we're thinking of the 1 as the square root of 1, which is the radius of the inner ball, right? Cubed. Well, that's really important. So that gives us the square root of 64, which of course is 8. So it's the same thing as 2 to the 3 equals 8, but it's written in a way that corresponds to the next level, which we substitute the implied unit multiplier of the 2 directions with the square root of 2 and cube that, and we get a square root of 512. And we do the same thing by substituting the square root of 3 for our implied unit multiplier and cube that, and we get 1,728 cubic units. Well, it's when we start looking at how these are related, for instance, we divide the 2D one by the 1D one, we find that that's related by the square root of 8. That goes into 1D goes into 2D, the square root of 8 times. 3D divided by 1D, square root of 27. So that then gives us some 1, 2, and 3-dimensional relations that we haven't used before. Try to express them here. 2 times the implied multiplier, 2 directions times 1 magnitude cubed is equal to 8. But that's the same thing as we just showed up here. If we substitute the unit 1 by the square root of 1, we get the square root of 64, and that is the same thing as the one above. They're identical. It's just a different way of expressing them. But then we come down here in the second dimension, and we substitute our multiplier with the square root of 2, and we get the square root of 512. But that's the same as if we took the square root of 1 multiplier and multiplied it by the square root of 8. If we do that, we're going to get the second, in other words, we took the first dimension, multiply it by the square root of 8, we'll get the second dimension. And the square root of 8, of course, is the square root of 2 to the 2 cubed. And then we take the square root of 3 cubed and multiply it by the 1 dimension, and it gives us the third dimension. So now we have, you got to understand, I don't know, I may be nuts because I'm not a professional, right? And a lot of times they call us cranks and things. So somebody could really correct my understanding here. I'm just being honest, an honest investigator trying to talk shop here. But this is amazing. This is just like, if you multiply a number 2 to the third times 2 times, well, let's take 2 because we always using that. 2 to the third times 2 to the 1 is 2 to the fourth because you have to add exponents. But if there's no such thing in our physical reality, because we don't have 4 dimensions. So we can see this disconnect between geometry that has the 3 dimensions that we observe and numbers, which doesn't have that constraint, except in the Tetraktys, when the dimensional and the directional information is taken into account. But here, we're multiplying the one-dimensional unit up here by the square root of 3 cubed, and we get the 3-dimensional unit. And here we're multiplying the unit ball, that we'll call it. It's a volume, see, because it has the exponent of 3. It's a volume, but we're multiplying it times the square root of 8, and we're getting a 2-dimensional volume, if we can put it that way, meaning it's got a radius of the square root of 2. But it's, I hope I can, it's hard to make that clear, but think of that 2-dimensional frame defining that red ball. It's identified with 2 dimensions, that ball, and this one's identified with the 1-dimensional black ball. So, and this one with the 1-dimension, or with the blue ball. They're all 3-dimensional volume units, but it's identified with that color blue. And here we're getting it by multiplying the unit ball by the square root of 3 cubed. So that's really important, I think, to understand. Now, I may be corrected and shown to be really dumb in all of this, but there it is. We'll see. Now, so in putting it in words then, we can say this about discrete and continuous identities, at least in this 2n cubed progression. We can say that it can be demonstrated that the LC composite progression of discrete magnitudes is equivalent to a corresponding LC composite progression of continuous magnitudes if the implied unit multiplier of the 2 directions in each dimension is replaced with the appropriate radius unit and then multiplied by the appropriate constant, the square root of 2 cubed or 3 cubed. Now, that might be, that's up for challenge. Somebody can point out my fallacy here, and it wouldn't be the first time. I make some stupid mistakes, but I'd rather make stupid mistakes that get me to the next level than not to do anything at all. So anyway, this is where we're at with this scalar, new scalar mathematics. And so we present then the new, what we would call, I guess, LC algebra. the LC's n, that's the n in the LC in its 3 dimensions, is distributive, because no matter how we add up the numbers for n, whether it's a times b plus c or a times b plus a times c, for instance, it will still come out right. And same way, it doesn't matter the order of the operations. When we're subtracting, a times b minus c is also equal to a times b minus a times c. So we can distribute these numbers in any way. And I might point out at this point that we lose this in the imaginary number and the rotation of the waves. That property is lost, this distributive property, because you don't have a point that you can call. You arbitrarily can choose one, but in the numbers there's no zero. Anywhere along the circumference of the circle can be the starting point, and then you can go around 360 degrees and return to it. So the distribution here, the order, if you will, is not implied in the complex numbers. So we lose this distributive property in the complex numbers. Then if we move up to the quaternions, we lose this commutative property, where if you have a plus minus b equal to minus b, or if you want it to be equal to minus b plus a, where you reverse the order of the terms both in multiplication and addition, it doesn't work. So you lose this commutative capability. There is a lecture by John Baez that's on our website under LRC. Well, I think it's on the LRC Physics YouTube channel as well. You really need to watch that, because it really explains how then when you go to the octonions, which is the 3-dimensional level of vector algebra, the normal algebra, you lose this associative power that we don't lose. In other words, for us, it doesn't matter if you take a plus b plus c, it's going to equal the same thing as a plus b plus c when you group b and c together instead of a and b together. But that's not true for the octonions. They lose the associative power, and they've lost the commutative power at the 2-dimensional level with octonions, with quaternions. And with the complex numbers, which is we might call it the 1-dimensional, they change the meaning of the word dimensions. But you can see that this would be 1-dimensional if you look at it in geometric terms. The complex numbers, the quaternions are 2-dimensional, and the LCs are 3-dimensional. And so you lose these properties with them, but you do not with us, with this scalar algebra. In other words, the last bullet here, the LC algebra is completely distributive, commutative, and associative. So that's really important to understand, and that's the end of our presentation of scalar mathematics. And I hope it's made sense to you. There's a lot more to say about it. This is an introduction only, of course, and we will have this up on our website. And then next week, I don't know if I'll be able to do it this Saturday because of some other commitments that I have, but if I can, I will, and we will take it to the next step. But feel free to comment and in the section below, comment section below, or on our website, or however you'd like to comment, but and point out anything that you might see here that's out of order. But in this, we are planning on being able to analyze our equivalent to the standard model particles here, so that we can see how, for instance, these two, the positron and electron, if I move the electron here and the positron interact, and why the proton, which is made up of two of these and one of the downs, which is, chairs in the way, but anyway, right, all the interactions of these particles we need to explain, but we need to explain them not as the LST community has in terms of vector algebra, where things are moving, whether they're moving around the circumference of the unit circle or whether they're moving in some other way. Their idea of motion is a change of location. Our idea of motion is a change of size or change of scale, an oscillation of a volume, if you will. And that's going to require a whole different algebra. And hopefully this is going to be at least the beginning of that. But there it is for what it's worth. And I hope it has been worthwhile. And so I'll bid you adieu until the next time.